In this video, we're continuing our discussion of methods to solve systems of linear equations. Again, we are talking about iterative methods to solve linear systems, and in particular, in this video, we're going to talk about the Gauss-Seidel method. So the Gauss-Seidel method offers a slight modification to the Jacobi method, which can allow it to converge faster. In the Gauss-Seidel method, the system is solved using forward substitution so that each component uses the most recent value obtained for the previous component. This is different from the Jacobi method, where all of the components in an iteration were calculated based on the previous iteration. So let's consider our linear system AX equals B. The left-hand side can be decomposed into the sum of two matrices, U and L. So A is equal to U plus L. As you can see, U is an upper triangular matrix with 0 diagonal components. So all of the components along the diagonal are equal to 0. And L is a lower triangular matrix with its diagonal components equal to the diagonal components of A, as you can see here. If we start with non-zero diagonal components for our matrix A, then L can be used to solve the system using forward substitution. So we start with our system AX equals B. We write A as the sum of U plus L, where U is an upper triangular matrix with zeros along the main diagonal, and L is a lower triangular matrix. Then we can rearrange the equation as shown here, where we have Lx is equal to B minus Ux. So you can see that x appears on both sides of the equation, so we have to use an iterative, so this sets it up as an iterative approach to solve for x. So we'll use this equation to find x at iteration k plus 1 based on iteration k. And we can solve for this x here using forward substitution, using the approaches that we talked about in the previous sections. So using forward substitution for this equation, Lx at iteration k plus 1 is equal to b minus u times x at iteration k. The ith component of x, so xi at iteration k plus 1, can be computed as shown here. So 1 over aii times b minus this sum of aij xj at iteration k minus this sum of aij xj at iteration k plus 1. And you can see the difference in the limits of the sum between these two cases. So let's look at kind of how this came about. So if we recall for the system that was written Lx equaled B in the previous discussion where we talked at the LU decomposition, for example, if L is a lower triangular matrix, we wrote the general formula for the forward substitution as shown here. So xi, or the ith component, is equal to 1 over lii times bi minus this sum from j equals 1 to I minus 1, lij xj. Now our system is a little bit different. So we don't just have b on the right-hand side, we've got all of this b minus ux at iteration k. And u times x is just going to give us a vector, so this is still just a vector. It just has a little bit more to it than just b. And we also know that a is the sum of our L and our u. So here we've got our L, our lower triangular matrix, and our u here. So a, if we put all those components together, we can write a as shown here. So now this is the form of the forward substitution that we just wrote on the previous slide, so we can see kind of where these components come from. So this is the ith component of u times x at iteration k. That's why we have this extra sum. So the b is just the b. We've got this ux at iteration k becomes this sum, and then the sum that was in our original forward substitution equation is still here in its similar form. Now here we're writing this with uij and lij and lii. And on the previous slide, these were all written as a. And you can see that since we know that a is equal to L plus U, so if we write L a in this form, then we can just write this all in terms of aij directly. So this equation can actually be written by replacing here the L and the U with a. So this is an iterative method similar to the Jacobi method, and the same stopping criteria as used in the Jacobi method can be used for the Gauss-Seidel method. So the iterations are performed until epsilon r is less than or equal to epsilon s, where epsilon r is our approximate relative error, is given as the norm of the current iteration minus the previous iteration divided by the norm of the current iteration. So let's look at the same example that we considered in the previous section for the Jacobi method and see how the iterations progress using the Gauss-Seidel method. So we have our system ax equals b defined as shown here, and we want to find the solution x using Gauss-Seidel method with an error threshold of epsilon s is 0.0001 with an initial guess of 111. So this is our system ax equals b. First thing we want to do is rearrange the system to the form of the Gauss-Seidel method. So Lx equals b minus ux. So here our u and our L are given. Again, u is the upper triangular matrix with zeros along the main diagonal, so we take these components of A, and then L is everything else, so it's the lower triangular matrix with the diagonal given as the diagonal components of A. So then we can write our system as Lx is equal to b minus ux, as shown here. We need to use our initial guess to calculate the new estimate. So we're going to have L times x1 is going to be b minus u times x0, or our initial estimate. And you'll notice that in the forward substitution, the value of x2 at iteration 1 uses the value for x1 at iteration 1, not iteration 0. So it uses the current iteration rather than the previous iteration because we've already calculated it when we do the forward substitution method. And so x3 uses the values of x2 at 1 and x1 at 1, rather than using the previous iteration, which was done with the Jacobi method. So you'll see kind of how this works. So using forward substitution, we can find x1 is equal to, so we use this first row as our equation. So 3 times x1 at 1 is equal to 7.85 minus negative 0.1 times x2 at 0, which was 1, minus negative 0.2 times x3 at 0, which was 1. So from this we get that x1 at iteration 1 is equal to 2.716667. Now for the second row, we have 0.1 times x1 at 1. So now we already know what x1 is, so we can take this value and plug it in here rather than using the previous iteration. Plus 7 times x2 of 1 is equal to negative 19.3 minus negative 0.3 times x3 at 0, which was 1. So this is our previous iteration. So x2 at our current iteration is equal to negative 2.7531. And then to find x3 at our current iteration, we again will use our current values for x1 and x2 because we've already calculated them in our previous steps within the same iteration. So from here we find that x3 at our current iteration is 7.00344. So now we can find the approximate relative error using our definition here. So the approximate relative error for this estimate is our new values minus our old values divided by our new values. So the norm of xi minus xi minus 1 divided by the norm of xi. So this is equal to 0.9106, which is greater than our error threshold. So that means we increment our counter and continue. So we go back to the previous slide and update our estimate again using our forward substitution method. So this shows the output for the remaining iterations using the Gauss-Seidel method. So the first column here shows the iterations, 1, 2, 3, 4, and then these show x1, x2, and x3 at each of the iterations, and then this is our approximate relative error ER, or epsilon r. And so you can see after 4 iterations, we find the same result, 3, negative 2.5, and 7. And after the procedure is done, our approximate relative error is 3.4 times 10 to the minus 6. So you can compare this with the Jacobi method. The results are, at each estimate is slightly different. The final result is the same, and the error here at the final result, at the 4th iteration, is smaller than it was with the Jacobi method. So in this case, it's not obvious, but the Gauss-Seidel method can converge faster than the Jacobi method. In this case, they both take the same number of iterations, but the error term for the Gauss-Seidel decreases a little bit faster. And in other examples, the difference may be more obvious. Now, important thing to note about the example code that I provided, Gauss-Seidel.m, it's written to emphasize the approach and explicitly works with L and U. However, the algorithm can be programmed more compactly, for example, if we use the forward substitution form that was presented on slides 8 and 9. So you can try to reprogram the method using that form of the forward substitution method if you would like.